Hi everyone, and welcome to my channel. If you're new here, I post videos on key maths topics to help with studying and revision. Today, I will be running through part 2 of this video on introduction to mathematical proofs. If you haven't watched part 1, I will share the link to that video. But today, I want to focus on two key types of proof, which are proof by contradiction and proof by induction. If you remember from part 1, I started out by outlining the most common types of mathematical proof, and then went through some examples on proof by deduction, proof by counterexample, and proof by exhaustion. Today, I want to talk about proof by contradiction and proof by induction, because these methods are a little bit more advanced. So starting with proof by contradiction. So with proof by contradiction, when we're presented with a statement that we need to prove, we start by assuming the statement is not true. Let's take an example of this. Suppose that x squared is an even integer. Then x must be even. This is the statement that we're trying to prove, which I've highlighted here as the original statement. First, we assume the contrary, and that is we assume that there must be an odd number x for which x squared is even, and I've referred to this as the new theory. We then work through this. So if x is odd, from part 1 of the tutorial, we know we can write this as x equals 2m plus 1 for some integer m. Thus, x squared can be written as 2m plus 1 in brackets all squared. And then if you expand this and rearrange this and then reapply brackets, we can write this as 2 in brackets 2m squared plus 2m close brackets plus 1 at the end. And this means that x squared is odd. If x squared is odd whenever x is odd, this contradicts the assumption that we made for our new theory, where we assumed that there does exist an odd number x for which x squared is even. So we have contradicted our new theory. And because we have contradicted the new theory, this means that the original statement must be true. And therefore, if x squared is an even integer, then x must be even. One thing that I didn't highlight in part 1, but I think is useful to know, is when you're writing a proof, particularly at advanced levels, one of the tricks with the notation is to put a little square at the end, and that just highlights the fact that you've reached the end of the proof. Let's run through another example of proof by contradiction. We can actually use this method to prove a key maths theorem. The theory that we have here is that the square root of 2 is irrational, and it cannot be written in the form m over n, where m and n are integers. Again, this is our original statement, and so we first assume the contrary. And here then we assume that the square root of 2 does equal m over n, or can be written like that, where m and n are non-zero integers. And this quotient or fraction is stated in its simplest terms. Taking our new theory, if the square root of 2 can be written as the fraction m over n, then if we square both sides, we get that 2 must be equal to m squared over n squared. And therefore, if we multiply both sides by n squared, we get that 2n squared equals m squared. Therefore, m squared is an even number because it is a multiple of 2. If m squared is an even number, then m must be even, and that we have just shown or proved in the first proof. So we can replace m with 2k. Thus, 2n squared equals 2k all in brackets squared. And if we expand out of the brackets, this gives us 4k squared. Therefore, n squared equals 2k squared. And so n squared is also an even number. Because n squared is an even number, as before, n must be even. So we can replace n with 2j. This then gives that the square root of 2 can be written as the fraction m over n, which can be also written as the fraction 2k over 2j, which we can then simplify. But this is a contradiction because we assumed at the beginning that m over n was stated in its lowest form. And yet, working through the new theory, we've come up with a solution that shows 2k over 2j. And so we have contradicted our new theory. And thus, the square root of 2 cannot be written as a fraction m over n, where m and n are integers, and hence it is irrational. Proof by induction. With proof by induction, we are trying to prove that a statement is true for all natural numbers. Although there is some debate as to whether 0 is a natural number or not, I would think of the natural numbers as starting from 1 onwards, so 1, 2, 3, 4, etc. A good analogy for proof by induction is that of the domino effect. If you push the first domino over, this knocks over the second domino, which in turn pushes over the third domino, and so on. So what I mean by that is when we start with a proof by induction, first of all, we prove that the statement is true for a base case, usually where n equals to 1. Sometimes you might use a different base case, but in general, you would use n equal to 1. And then you assume that the statement is true for an arbitrary value n equal to k, and we call this the inductive hypothesis. Then we use the assumption to prove that the statement is also true for n equal to k plus 1, and this is referred to as the inductive step. Then we give a concluding statement to explain how the previous steps have proven the result. So what I mean by the domino effect is if you have proved a statement is true for 1, and you prove a statement is true for n equal to any number k, and then any number equal to k plus 1. So in other words, you show that two numbers in sequence, the proof holds true. And you have started by showing that it's true for what would be normally the first number, n equal to 1. Like a domino effect, the proof is true then for all the natural numbers. And at the end of the proof, we generally state a concluding statement to show or to explain how the previous steps have proved the result. Proof by induction is particularly useful for showing that expressions are divisible by a certain integer. So let's look at an example of this. Here we are asked to prove that 3 to the power of 2n plus 7 is divisible by 8 for all n where n is a natural number. Step 1. Well, let's start with the base case. If n equals to 1, then we have 3 squared plus 7, which is 16. 16 is divisible by 8. Thus, the statement is true for the base case. Then we move on to step 2. So assume the statement is true for n equal to k. We substitute in k. So we have 3 to the power of 2k plus 7 equals 8m, some kind of multiple of 8. And I've added in brackets here a rearrangement of this equation, and we'll need this in a moment. For n equal to k plus 1, we have 3 to the power of 2 and then in brackets k plus 1 plus 7 at the end. And we can expand out of the bracket. And we know from the laws of indices that this can be rewritten as 3 to the power of 2k times 3 squared plus 7. You can see highlighted in green, this is the key point. We have managed to rearrange this expression so that we have a term 3 to the power of 2k. From our assumption that the statement must be true for n equal to k, we know that 3 to the power of 2k can also be written as 8m minus 7. So the trick with proof by induction is to manipulate the expression for k plus 1 so that it is expressed using the terms in the statement where we assume that n equal k. We can substitute that in to our equation. We can expand and rearrange. And this allows us to factorize where we have 8 outside of the brackets and then m times 3 squared minus 7. And this is a multiple of 8. So to conclude, we have shown that if the statement is true for n equal to k, then it is also true for n equal to k plus 1 because we found a result which shows that it is divisible by 8. And since the statement is true for n equal to 1, then it must be true for all the natural numbers. Because if k were equal to 1, n would be equal to 1 plus 1, which would be 2. Whereas if k was equal to 2, then n would be equal to 3, and etc. So let's take another example of proof by induction. A lot of proof by induction questions that you may be presented with would be similar to the previous example where you're showing that an expression is divisible by a certain number. But here we have a slightly different example. Here we're asked to prove that the sum of numbers in the sequence from 1 to n for r squared is equal to 1/6 times n times 2n plus 1 times n plus 1 for all the natural numbers. If you've not seen this notation before, this n, that just means that's the notation for the natural numbers. We're just saying for all numbers that are natural numbers. Step 1. As before, we need to start with a base case. If n equals to 1, then we have on the left-hand side of our equation, r squared would be 1, and we only have one term, and that equals to 1. And on the right-hand side, we would have 1 as well. So the statement is true for the base case. The second step then, as before, suppose the statement is true for n equal to k. Here we have the sum from 1 to k, r squared equals the equation as before, but with k substituted in. Then we create an expression for n equal to k plus 1. So that is, we have the sum of from 1 to this time k plus 1 r squared. If you're in a series, if you're summing from 1 to k or 1 to k plus 1, the only difference would be the term that is k plus 1. So this can be written as the sum of 1 to k r squared plus k plus 1 squared. And why do we do that? Well, as before, we refer back to the statement that we wrote when we assumed that it was true for n equal to k. Because what that means is we can then substitute the section that is true into the statement for k plus 1. And this allows us to eliminate with the sum from 1 to k. And instead, we just have a nice expression here. And then we can rearrange this expression so that we get an output that looks like the equation on the right-hand side at the beginning of the example. So we have 1/6 k plus 1, 2k plus 3, k plus 2, which, if n equals to k plus 1, equals 1/6 times n times 2n plus 1 plus times n plus 1. So we have shown that if the statement is true for n equal to k, then it is true for n equal to k plus 1. And since the statement is true for n equal to 1, it must be true for all the natural numbers. I hope you found today's video, which has run through some examples of proof by contradiction and proof by induction, helpful. There are many types of proof, and there are many examples that I could have used to demonstrate how these proof methods work. If you would be keen to see more examples, please let me know in the comments and I can create additional videos on proofs. But I hope you've enjoyed it and thank you for watching.